Okay.
All right. So my basic plan for the moment is really just to show you better pictures than I showed you last time, and perhaps more optimistic, convincing, hopefully convincing suggestions that things are working here reasonably well. Well, I mean, let me just preview the pictures a little bit. See, that's a very nice looking picture. And this is also a very nice looking picture.
Yeah. Are those the same two guys that you've shown before?
I think so.
Anyway?
I think so. I didn't quite have time to check it. I mean, but so most of my presentation for today is showing you this picture, and skip over this one. That doesn't matter. I don't think it matters. And this picture. And I believe that these are in the same Grothendieck-Teichmüller orbit, that they actually constitute a Grothendieck-Teichmüller orbit. And that following along the lines of what I'm doing in this program, we should be able to actually prove pretty carefully that this actually is a Grothendieck-Teichmüller orbit. And so, like, I was doing things in very helter-skelter fashion last time. And like I had, notably at one point I had a mathematical program that numerically found 751 solutions of the equation that I was dealing with. And then I searched through them by hand and I found the two that I wanted out of the 751. Wasn't quite sure what the other 749 were for. Today, it's a vast improvement. Today, you could see that, where is it? It's like, see, there's only like 22 solutions that it found. And they're basically the two that I want. And in fact, it's better. It's really better than there being 22. If you stare at these 22, you can see that a lot of them are repetitions of each other. And you can also see that some of them are degenerate in very clear ways, so that we know that we want to get rid of them. And so, in fact, I think it might be, I still need to check this when I get home, but I think it might be that this is really, in some sense, doing the optimal thing. That it's really showing us that there really is just basically these two solutions to the same equation. And, and the equation is in rational language, so that this would have to be, I think, if I understand it, a Grothendieck-Teichmüller orbit. And again, these designs are kind of, right, I call them Gaussian designs because they're based on the Gaussian elliptic curve. So I haven't told you yet what was like magic trick that helped me, because it's not like I really figured out the right way to do things. It's more like I got lucky. I discovered an ad hoc trick that really cut down on the number of solutions and cut down on the solution space. And well, so let me tell you what this ad hoc trick was. And one thing that makes it ad hoc is that it doesn't even work in the Eisenstein case. I mean, again, it's hard for me to switch back and I'm not very, I don't have a great facility with switching back and forth between different things I want to share on the screen here. So I'll just try to describe, instead of showing you the picture, I'll try to describe these two Coxeter diagrams, the one for the Gaussian designs and the one for the Eisenstein design. So the one for the Gaussian designs looks very symmetrical in a way. It's a 3 dots in a row, 2 edges between them, and they both have the same label on them, 4.
Yep.
And that's basically because, so that symmetry of just sort of flipping the diagram, that comes from the fact that it's sort of hard to tell the difference between the Gaussian integers and the dipoles between the Gaussian integers.
Yep. Uh-huh.
Whereas with the Eisenstein integers, you can easily tell the difference. You know, one has like a 3 label, the other one has a 6 label or something like that. The dipoles between the Eisenstein integers are not the same as the Eisenstein integers, even if you shift them or something like that. So, so my trick is to exploit this symmetry. So, you know, in my setup, well, you know, I usually try to follow this convention where I have the green. Actually, I forget what my convention is, and but it's something like, it might be that the red vertexes are the Gaussian integers themselves. The green ones are the dipoles, and what the hell are the blue ones? The blue ones are like
The edges.
Yeah, are they barycenter? I guess since they're vertexes, they must be barycenters of edges or something like that.
Mhm.
I guess that's right. And so basically what I asked the Mathematica program to do was to only search for solutions that have hopefully somewhat obvious kind of symmetry between the flipping of the red and the green. And so again, I mean, there's so many things I'm ill prepared for here today. One of the things is I didn't finish putting in the colors here. So, you know, I'm talking about these red and green and blue vertexes. You can't see them in the pictures at all. I mean, you can see the places where there are multiple lines crossing and vertexes go there, but there also are a couple of places, I think precisely a couple of places, where there are blue vertexes and you can't really see them because they're, you know,
Oh, I see.
they are non-critical points whose value gives a critical value. Right?
I don't know. Oh, yeah.
You know, a critical point is a critical point, and a critical value is the output at a critical point. But just because a value is a critical value doesn't mean that the whole fiber over it consists of critical points. There could be non-critical points that live in the fiber over a critical value.
Uh-huh.
And then that happens in these. And basically, I mean, what that, another way to think of it in terms of the Young diagrams that are corresponding to permutations here, it's just saying that we have some rows in the Young diagram that are a single column wide or something like that.
Yeah. About this Young diagram business.
Yes.
So any two designs that are in the same Grothendieck-Teichmüller orbit have got to have the same Young diagrams.
Yes, or the same vertex census, as they say it, keeping track of the But it's also the same constancy class of the permutations at the generators of the critical values. Yes, go ahead.
But not conversely. But you're saying that in this case, you may be lucking out that what you're classifying as all the ones with the same vertex census.
Yes.
And it could conceivably be a union of the thousands of
that's right.
Teichmüller orbits, but you're saying that you're just
that's right. In this one example,
enough.
It really looks like it's pretty much just a single Grothendieck-Teichmüller orbit. And yeah. So there are definitely some lucky things about it, but
so why do you even know that these two guys are in the same Grothendieck-Teichmüller orbit? What's your reason for thinking that now? I forget.
I still need to go home and think if that's really true. I should say that, you know, I guess we talked last week, and then in the intervening week, I got really busy and really enthusiastic on writing these programs, improving the programs over the previous primitive versions that I showed you last time. And then I just made so many stupid mistakes, had so many programming bugs. I didn't even want to talk today because, you know, this morning it was still all screwed up. So, you know, suddenly this morning the program started working and I started getting these nice pictures. But I didn't really have time to check that it's really, really working. But I think when I go home and check, I think we'll see that it really is working and it will give an answer to the question that you just asked. And so let's see, the question that you just asked, if I recall, is what makes me think that these are in the same Grothendieck-Teichmüller orbit? And so let me give you a very ridiculous plausibility argument that I think might be correct, but I need to go home and check if this really makes sense. So I've got this, I've got this system of equations, and it's got the equations in the equations in the system have purely rational coefficients, but the solutions to the equation, and mostly it has to do with the solutions, has to do with the locations of the vertexes and stuff like that. So Mathematica offers an option. You can either go for a numerical solution or you can go for a symbolic solution. And I've been switching back and forth between both of them. And when I use the symbolic solution method, it actually gives me these things. You can, some of them are ridiculously elaborate formulas that have square root symbols in them, and you can see all these square root formulas. So you can get a sense of what kind of irrational number these are. And so that since these irrationals are showing, these radicals are showing up in the solution to this equation that is purely rational coefficients, I think we'll be able to tell. I mean, I need to examine these formulas and look at all the radicals. I mean, for one thing, I should be able to look at the formulas and see that they're actually the same formulas, just with the, different signs on the radicals. Because I think in this example, it turns out to be all square roots. So I think you might just have to check. So that's one.
Yeah, I was just wondering how you plan.
Yeah, the work isn't done yet, but I think.
But that's a good. I mean, that's a good way, partially because that's a way that sort of should generalize. I mean, it may be more hard work, but you can.
That's right, and it's also a fun way because it exploits Mathematica's symbolic solution method, and I also want to exploit their numerical solution. I mean, I don't want. I've probably made this clear. I don't want to give any kind of advertisement for Mathematica at all because, we could just talk all day about all the things wrong with Mathematica. But it's actually, we're exploiting some things, some very fun things about working with Mathematica. So
also one other stupid little comment you'd mentioned.
Yeah.
One of these two guys had bilateral symmetry, and now it.
Yeah, now
it's obvious. Well, you went away from it, but yeah,
that's right. That's right. And in fact, now they both have such explicit. Where did it go? This is the one of them, and this is the other one. Well, this has a different kind of bilateral symmetry.
That's true.
And in fact, I mean, and I've gotten so used to the idea that both of them have some kind of bilateral symmetry. Again, I'm not sure if bilateral is the right word or skew bilateral symmetry.
This is some kind of skew thing, and this skewness is like visible in the original style of picture.
Well, but we have to be careful about that because the one of these pictures that is equivalent to the one from last, matching up, corresponding these two now, last time. I'm not even sure which one corresponds to which one. Because,
gosh. That would be crazy.
Partially because there's some hidden symmetry, and no matter how you draw it, I think there's some hidden symmetry. Unless you make like a 3D model of it or something, I think there's like there's a symmetry. There's a symmetry between the interior of this circle and the exterior of this circle.
Oh, okay. Yeah, you're right. Oh no, so they both have a Klein-4 group. Well, that one had a Klein-4 group symmetry.
This looks Klein-4. I don't know. I mean, I haven't even figured that out.
Okay.
But it should be a lot of fun trying to straighten out that kind of issue that you're talking about now. Yeah, I mean, I have some pictures. Let's see. Can you can't see my face right now? Let's see.
I can see your face, but
I'm not sure if anybody else can see the face.
I can just barely see that stuff. It's better to get rid of the screen sharing if you want to really show me something.
I know, but it's too much work to change the screen share. So I just wanted to show you just a ridiculous hand-drawn thing here, if you can see it at all. You can see those hand-drawn things, right? Yeah. So part of my homework is to figure out which of these hand-drawn things correspond to which of these Mathematica-drawn things.
Oh, okay.
And it's not at all obvious to it. It's not at all obvious. So Yeah, so like I say, the ad hoc lucky thing here. I mean, one thing about that is, like I've sometimes been saying in recent weeks, I've been saying that, first you write down some of these systems of equations, and then they may not narrow it down to a single Grothendieck-Teichmüller orbit. So you perhaps try and think of anything else that you can say that will narrow it down further, still speaking the rational language. And what seems to be going on here is that we kind of lucked onto something that we can express in rational language that does narrow it down a whole bunch, or at least it seems.
Sorry, which is what?
Which is this symmetry property, this, this compatibility with the red-green symmetry. So that, I still think that that's a sort of lucky coincidence. I don't think there's anything terribly fundamental to it. Well, there's probably something interesting about it, but it still seems like a lucky coincidence. Like I say, I don't know how to generalize it to the Eisenstein case even yet. But so yeah, so these pictures here, especially this picture here.
Are you claiming that all Gaussian designs have that?
Yeah, that's a good question. I
Because
didn't decide that yet.
you could.
It almost seems like it might be true. What?
Yeah. You could fear that although the Gaussian lattice has that symmetry, that you could like do things to it that break the symmetry. I don't know.
Sure, and it might even be more fun, even rather than fearing it. It might be more fun that way. But it might be that the less fun thing happens. It might be that all Gaussian designs. I just didn't figure out the answer to that question yet. That's a good question. Do all Gaussian designs individually have this red-green symmetry? Let's see, I guess, did I emphasize yet that how annoying it is that I haven't put in the colors of the vertexes yet? That's just another thing that I didn't get around to doing yet because the program was driving me up the wall, but it just wasn't working. Yes. And so most of what I'm doing here is just propaganda by showing you these two pictures. I also tried to give you a little bit of propaganda by claiming that Mathematica is giving me these expressions with lots of radicals in them. And it's even more annoying that I can't show you those radicals because Mathematica wastes a ridiculous amount of time into being able to display formulas with radicals in them. But I'm just not getting it to work right now. So I can't show you these formulas with radicals in them, but it's really true. You can see I don't know if you can see that on the screen. It's a very annoying way of
a little thing.
Yes, and it doesn't use the radical symbol. It uses some other thing. Yeah, that would be right. That would be nice propaganda too. If I could show you some of these formulas, some of them, the formulas are kind of ridiculous looking. They have a lot of radicals in them. So it should be fun trying to analyze their Galois ambiguity. But right, mostly this is just propaganda pictures to try to convince ourselves that we're on the right track here. So before I hand it over to you, let me just say, what should I really actually be talking about instead of just showing you propaganda pictures? Well, so one thing we'd like to do is, so these are things that hopefully maybe I can do next time or something like that. So one thing I should do is I should get this stuff that I'm showing you here now with Mathematica doing stuff. I should, conceptually mesh these pictures and these calculations and these formulas with some explicit formulas that we probably want to work out for ourselves, sort of on pencil and paper or something like that, where we write down, more or less standard or somewhat standard equations for the Gaussian elliptic curve, system of equations, single equation for the Gaussian elliptic curve. And, since I write all of these Gaussian designs are sort of in some way distorted images of the Gaussian elliptic curve. So we may, well, we may want to try to work out explicitly. I think we've already tinkered with this. We've already played around with it a little bit, experimented with it a little bit. trying to write down explicit formulas for like the 3 torsion points on the Gaussian elliptic curve, which are the inflection points or something on the traditional picture of the Gaussian elliptic curve. And we can try to check whether calculations that we do by that method, and again, we may want to get, we may very well want to make those calculations computer assisted as well. But we want to get a consistency check to see that those calculations agree in some certain ways with the calculations that I'm showing you here today. Or again, the calculations that I'm not quite showing you because you can't quite see them because the radical signs aren't displaying properly at the moment. But so that's a thing to that's a thing that's, you know, on the agenda of more serious things I should actually be doing instead of just showing you pictures. And what are they going to say? Well, so that in that project that I was just describing to you, that project, upcoming project that I should probably try to demonstrate for you, if I can get it to work, is I mean, it's a very, in some ways, it's a very gritty calculational thing, but there's actually some very nice conceptual viewpoint to clarifying how it should work. And so that should come into what we're going to try to do. And that ties in with the other thing that I should really be telling you more about, which is, so just at the end of the last discussion, I started talking about this paper that I'm reading by somebody whose name, not sure how to pronounce it, Thomas Wilwacher, something like that. And this is the beginning of my attempt to finally actually read up on Grothendieck-Teichmüller theory instead of just trying to reinvent everything, fumbling around by myself. And it's looking really interesting. I've been really distracted from it the last week because I could spend so much time debugging computer programs in the last week. But there's really interesting stuff going on trying to understand this paper I'm reading. And I'm not sure
okay, yeah,
what to say about it at the moment. Go ahead. What?
Yeah, I looked at it but I didn't really have time to really look at it. So
right. But, I mean, I've only begun to look at it.
There was these things
really
called course notes. It was this paper called Course Notes on Grothendieck-Teichmüller theory.
Say it again. The name of the paper is Course Notes or something?
Yeah, I mean,
I didn't even notice the Course Notes part. I just saw a title that said something like, I thought it said something like, maybe Introduction to the Grothendieck-Teichmüller
okay.
group.
Yeah, that sounds about right.
Grothendieck-Teichmüller theory.
Well, we're talking about the same thing if it's a course he taught, and I think it is, yeah.
All right, we should try to clarify that.
Yeah, you know, he might have written 2 things about it.
Sure.
Yeah.
There might be different versions of each other or something like that. So do I have anything else more to say right now at the moment? Again, if I might try to say more at the end of today, but
yeah, you can say more at the end.
But for the moment, I think I'm going to again declare victory, saying that things are actually right. I mean, we still need to prove things more carefully, and not just prove things more carefully, but also prove things more conceptually and really understand conceptually what's going on here. Again, that has a lot to do with this paper that I was just talking about, but I don't think everything tells me to say about that at the moment. So I'm just going to stop sharing the screen, I think. And then you're going to start talking about stuff?
Yep.
All right, let me stop.
So
Stop. Wait a minute, where's the button? Did I do that? Okay.
Okay. Well, I'm not. Yeah, I'm not terribly well organized here, but I'll just.
Sure. And you know, I have a guess that you're talking about the tenfold way.
Yeah, yeah.
But there's so many parts of that that I don't really know where you're going today with it today.
Yeah, well, I don't know where I'm going today either, but
Okay.
but anyway, so I'll do it nonetheless. So
Okay.
okay, so I've been digging into this idea that there are 10 superdivision algebras over the real numbers.
By the way, this is really helpful just drawing like this.
Well, I was gonna now.
Although
Yeah,
now you got me wondering if, is there really a significance to the way that you drew it here with the concentric stuff?
There sort of is supposed to be, although it's probably not too good.
Okay,
so
and if you want me to shut up more, you should let me know. But
yeah, I think
it
so.
sounds like we have a lot of time relative to, neither of us can think of anything to say. So unless you
Yeah.
really tell me to shut up, I might not. Go ahead. Yeah.
Okay, so so the fact that there are these 10 superdivision algebras means that when you have nice enough categories enriched over real supervector spaces, namely categories where every object is a sum of simple objects.
Again, I'm tempted to think that there's some definition of the general concept of two Hilbert space that you're talking about here, but maybe not.
Yeah, I like that, except that in a way, two Hilbert space, as I had been defining it, it's a bit overkill because it puts an inner product on the Hom spaces.
Sure. I mean, I was being very even slappier than that. I mean, two vector spaces.
Yeah.
So versus two
yeah,
Hilbert spaces.
so I have isolated what I think are the right class of categories, and I'm sort of annoyed that I don't yet have like a really snappy name for them. Like two bloody blahs. So what it seems that like so like one way to say it, that's sort of,
I mean, there are some kind of two modules, right? There's some kind
of well, they might be.
So there are vector spaces. They're two modules of these division algebras. I don't know. I'm sorry. Go ahead.
No. No, I mean, so the kind of category that I'm thinking about here is semi-simple categories enriched over finite dimensional real supervector spaces. So the Hom sets are these finite dimensional real Z mod 2 graded vector spaces, and the symmetry on the supervector space, on the category of supervector spaces, isn't showing up yet, because all we need is the monoidal structure to define enrichment over them. And you don't need the symmetry. You don't need, I mean, there's like these two famous symmetries on the monoidal category of supervector spaces, the one where you stick in these exciting minus signs and the one where you don't. But probably the one where you stick in the minus signs is going to become important at some point, but it's not necessary to define this class of categories, which I defined. And then semi-simple categories, people have different ways of approaching them. The usual way is sort of overkill, and you probably won't like it because and also Bruce Bartlett, who wrote the article on the NLab on semi-simple categories, doesn't like it, because the usual way is you say an abelian category where every object is a finite direct sum of simple objects, and simple objects in that context could be defined either as objects with no non-trivial sub-objects, or you could define them as having no non-trivial quotient objects.
Those are different?
those are the same
Oh,
in
those
the
are-
abelian case.
Yeah,
So in the abelianness, when you have a non-trivial subobject, you can mod out by it
Yeah,
and get a
yeah.
non-trivial quotient and vice versa.
Yeah.
So what Bruce Bartlett doesn't. So anyway, so that's fine as far as it goes. But yeah, Bruce Bartlett finds it unaesthetic or unnice in the way that you reminds me of you, because abelian categories are using a mixture of
yes,
limits and limits, and especially for semi-simple categories, you can define them perfectly well, only mentioning one of those. For example, just the co-limits. You don't need to. So there's like another way that you could define semi-simple categories.
yes.
So a simple object would have no non-trivial quotients, I guess. And then it would need to have, so every object, and you can define coproduct, and of course, and sorry, that's also in the doctrine of colimits. And so you want a category that has, I think, I probably don't know precisely what to do it this way, but it's something like every object is a finite coproduct of objects that have no non-trivial quotients. Maybe that's all there is to it, or maybe you need to put in a bit more. So anyway, that's a kind of a conceptual issue that could be important. But well, one thing is that I'm going to give some talks about this, and I don't think the people I'm going to talk to are going to be the kind of people who will thrill to those issues.
Right.
So anyway, so anyway, hopefully I can still explain to them, and also hopefully I just did explain to you what I mean by a semi-simple category enriched over finite dimensional real supervector spaces.
Yeah, I'm still, as you're talking, I'm realizing that I'm still fumbling over certain things here, but that's okay. I think I can clear it up because when I go home and stuff like that.
Uh-huh.
Go ahead.
So then when you have such a gadget,
Yeah,
then you can focus on the simple objects, and the simple objects will have as their endomorphism algebra a superdivision algebra.
yes.
And so there are 10 of those. And so what you get, so it starts out, let's just say, being like a set of 10 of them.
Yes.
And so then you see that all the objects in your category become graded with respect to this 10 element set, because you can just write them as a direct sum of the different kinds of the 10 different kinds of simple objects, and group them together in that according to their endomorphism algebras. And so then, okay, so then there are different ways to go from there. So one is that in fact that set of 10 superdivision algebras is actually a monoid in a natural way. And I will.
The set of 10 is a monoid. Okay.
Yeah. So there's this nice 10 element monoid, which we're sort of staring at here.
But did you say whether it's I should know this, but it's a commutative monoid?
It's a commutative monoid. Mm-hmm. And so all this becomes important when you want to consider these kind of categories that I'm talking about, but consider examples of them which are monoidal, or even say symmetric monoidal, so that you could talk about so the objects in this category are I'll call them 10 graded. So if you take two of these 10 graded objects, we'd like to think about how their tensor product will be again a 10 graded object, but we'd like it's going to work out nice if that 10 is a monoid, because then you can because there's like always a monoidal category of M graded objects in a large class of contexts when M is a monoid.
But there is something funny about that 10 not being a group, because I have a feeling that there are special things that you can do when you have a group there. And I'm
That's
not
right.
quite sure how much you want to be able to do those things here, or maybe you can get some mileage out of not being able to do them. But anyway, keep going. Yeah.
Yeah. So, well, that's really interesting. So instead of continuing on at that abstract level, let's maybe since I can't write, I have this picture of this 10 element monoid in front of us here. I might as well talk about it because it's really nice to get to know it pretty well. So it consists of two groups, this 8 element group on the outside and this 2 element group on the inside. And the 8 element group is Z mod 8.
Okay.
And the 2 element group is Z mod 2. And then the identity of the Z. So then you have to know what happens when you multiply a guy in Z mod 8 with a guy in Z mod 2. That's the only other stuff you have to know the multiplication.
Wait a minute. So you said the 8 thing has a cyclic structure.
Yeah,
and,
this
and,
is the
and you've drawn it
identity of
cyclic.
that.
You've drawn it cyclic.
Yeah, this is the identity of this.
And that's why you call it a
8-element
Clifford
group.
clock or something. What? Yeah, go ahead.
Yeah, yeah, and this is the 8 element. So the real numbers thought of as a purely even superdivision algebra is the unit of this 8 element.
But sorry, it sounds like you're telling me that R, direct sum R, is the negative of C.
Yeah, you have to.
We did talk about, the funny, great, funny grading, funny something on C.
Yeah, this is C with so what we're doing is we're walking around this clock. Well, yeah, okay, stop talking for a little while. So yeah,
Okay.
yeah,
Well,
I mean,
these are important questions. Go ahead. Yes.
Oh, yeah, I know. They're just happening at the wrong time. Yeah. So I'm just like outlining stuff. So I mean, yeah. So there's this 8 element group. There's this 2 element group, so the 8 element group, its identity is the real numbers, thought of as a purely even superdivision algebra. The 2 element group, it's the complex numbers, thought of as a purely even superdivision algebra. And so to describe the multiplication on this monoid, of course, we need to know how you multiply a guy in the 8 element thing with a guy in the 2 element thing. And so like the first thing to say is that if you like, is that the complex numbers sort of eat up the real numbers. So like if I tensor R and C, I get C. And so I get in here. So I'm just saying that if you tensor any of the outer guys on the outer black circle with one of the guys in the inner blue circle, you get one in the inner blue circle.
Well, so can I ask a question about this now, or should I shut up?
Well, let me just finish this remembering and describing how the how it actually goes. Let's see if I can even remember. So I think what you do is, so if we're trying to figure out like how I'll call it add now instead of multiply, how you add a guy in Z mod 8 with a guy in Z mod 2. And the answer is, you take the guy in Z mod 8, you work with it mod 2, so you further reduce it, and then you add it in Z mod 2 with your guy in Z mod 2, and so you wind up in here.
Right.
So you can see there's a kind of way of building a monoid, for example, from two groups and a homomorphism from one to the other.
Yeah.
It makes you take the disjoint union.
Yes.
And you multiply in this kind of manner where if you multiply two guys in the first one or the second one, you do it the usual way. But if you multiply a guy in the first one and the second one, then you map the first guy over to the second one. Okay, I'm ready for a question now. I mean,
I have a number of silly questions and comments. So one thing you got me wondering about here is, Well, so I first remarked how, these pictures are really helping me in following the discussion. But on the other hand, I'm also criticizing the pictures. I'm wondering if the pictures are right. I mean, like I said, you have this sort of concentric picture, but now I'm wondering if it should be more like a solenoidal picture, whatever the hell that means. Because I mean, like, to me, this picture, it almost looks like the 2 is a sub thing of the 8, but I don't see any way in which the 2 thing is a sub thing of the 8. It's more like, as you said, that the 8,
Yeah,
the 2 thing is a quotient of the 8. It's just,
yeah, it's true. So, I mean, maybe I should like draw it. Yeah, I don't know how to draw it though, but I should like draw arrows from every even one of these guys.
I still think it has something to do with solenoid, but go ahead. Yeah.
You're wrapping around an 8 element.
Yeah.
Wrapping around Z mod 8. Yeah, so I guess I could draw Z mod 8. I know, draw Z mod 8 is like a covering space of Z mod 2. It's be a pain in the ass to like draw it and make it look nice.
Sure. But I'm just trying to, understand. And I think I'm getting a sense of it. So as you say, there's this projection from the 8 down to the 2, and that's kind of how you multiply them together, that or add them together, that it just kind of right. It's like the complex thing is a contaminant, and it's like,
contaminant. I would say it's like it dominates the.
yes, as you say, yes, it's I meant contaminant in the sense of one bad apple.
Okay, yeah, right.
Or else I think of you can't go back or something like that. Let's see.
Yeah.
Right. Okay. Yeah. All sorts of things I have to think about. But let's see. What did I have another question or a comment here? Let's see what I was trying to say. Maybe I didn't, or maybe I've forgotten it. So go ahead. Okay. Yeah.
I'll march on. So one thing that seems sort of mysterious to me is that these, for example, I'll focus on the real ones for example, that these 8 superdivision algebras here are all Morita equivalent to the 8 different Morita equivalence classes of Clifford algebras. They're all Morita equivalent to Clifford algebras. And that was proved by this guy named Wall in 1964, actually. And this 8 element group here is called the Brouwer-Wall group of the real numbers, I guess. And
again, I feel like I really have to stare at this and really see.
I was going to dig into. Sorry, yeah, okay. Should I stop? I was like going from the top down into the detail. I was about to start like going into these 8 guys.
Well, I think I'm prepared to be conducted on the tour, but I just want to think about the general idea. Like, I mean, it is, unless I'm just not getting it yet, it's surprising how much individuality and idiosyncrasy each little stop on the tour has.
Yeah, well, they are really cool.
And like I say, I don't have an intuitive sense of why the inverse of this one is this one, and so it should be interesting. It would be fun to just try to figure it out completely by myself, but I think it'd be interesting to just hear your.
Yeah, I mean, there's lots and lots one could say about it, and I don't even remember all of it right away, but I'll remember some. So, but anyway,
this idea of Morita equivalence and matrix algebras, that all sounds very. Yeah, there are certainly things I've used to understand about this that I will hopefully understand again once you start talking. But go ahead.
Yeah, I mean, so one reason why this Morita equivalence stuff is so important is that I started out talking about the set of 8 real superdivision algebras, and then I made it into a monoid, and it's
And this is related to that way in which it's really a quotient rather than a sub thing or something like that. That, you know, we're really talking about a quotient, you know, like the Morita equivalence is like itself a congruence on this very large thing.
which very large thing?
Well,
Like all the
all the things, all the matrix, you know, this thing where you include
Yeah.
matrix algebras.
right. Yeah, that's right.
Right.
Yeah. So I was just gonna say that. Yeah. So if you started out just knowing about the superdivision algebras, you'd have no special reason to think that there'd be any good way to multiply two of them and get a third one. If you tensor them, you get this thing that's not a division algebra, but it's always turns out to be Morita equivalent to a superdivision algebra, but that fact is like not well, especially like, I mean, I guess that fact for like algebras, plain old algebras over a field is like some kind of Artin-Wedderburn theorem, or it's just once you know the Artin-Wedderburn theorem, it's easy to show this fact. That's what I mean. But here we're using an analogous fact for these super algebras, and that's making one thing that's making me wonder is like how much could we push this? So like the concept of, well, like here we're generalizing it to Z mod 2 graded. We're generalizing it from vector spaces over a field to super vector spaces over a field. There are people who've actually studied G graded vector spaces over a field. I mean, well, I know there's people who studied this particular issue for G graded vector spaces over a field, maybe like where G is an abelian group.
Yes. Yes.
And so it seems like there's some more general pattern going on where there's like some concept of like something like central simple algebras, or the fancier name is like Azumaya algebras, which are algebras that are like invertible with this after you mod out by Morita equivalence.
Yes.
And then there's some, and then we're seeing that like all of those are Morita equivalent to some kind of division algebras. I mean, I'm saying some kind of, because I'm imagining like generalizing this to you know, G graded vector spaces, but then it should be generalized somehow further to that, to just like some kind of class of categories. And so I haven't done any of that stuff. So anyway, that's part of why I'm like, find it sort of surprising or puzzling and interesting that we're getting this relationship between these division algebras and these central simple algebras and these, specifically these Clifford algebras. So okay, yeah, so that's like what I'm worrying about. But maybe I'll dive in and start giving us a tour. Let's see how far.
Well, but can I just make another silly comment here?
Sure, yeah.
So again, I still got this vague idea, which at first maybe didn't seem right, but maybe you know, this idea, the importance of Morita equivalence here is making me wonder about the idea of replacing each of these superdivision algebras by its module category in some sense. I'm not even sure what the idea is, but when you do it that way, and again, actually, I'm not even sure it even matters. It might, because if you replace, I mean, what kind of module? You could make it finite dimensional modules, or you could make it's connected. It's you know, it's irreducible module category. But that irreducible module category, that probably is really just secretly, practically just the original division algebra if you squint at it the right way. So maybe,
yeah, yep, you're right, that's true.
So maybe all these vaguely different viewpoints that I'm idly considering here aren't really that different. Maybe it's all really the same. Now that I think about it, but I was tempted to replace these division algebras by some kind of modular categories of them or something like that. But now it almost seems like it doesn't make any difference. It's really the same thing either way, and Morita equivalence sort of secretly knows all about that anyway. Sorry, that helped me, but I'm not sure it helped anybody else.
Yeah, yeah.
All right.
Yeah, it reminds me of things that I'm worrying about.
Okay.
Okay, I'll dive in on the tour here. Okay, so we start out with the real numbers, purely even graded in the even grade. Okay, then what we just start doing is we start throwing in more and more odd square roots of -1, which are all required to anti-commute with each other. That's if we do that, we get Clifford algebras. And they're written here, and we're just going up to Cliff 7, because by the time you get to Cliff 8, you get I believe 16 by 16 matrices of real numbers. And well, okay, there's one thing that's very confusing to me is that I actually have to worry about these algebras as super algebras.
Yes.
Very, very often. So you have to worry about, like, when you get to these 16 by 16 matrices, what about all the odd elements and the even elements? So I mean, as a plain old algebra, 16 by 16 matrices is Morita equivalent to R. But you say, like, wait a minute, but we're thinking of it as a super algebra. We've thrown in all these square roots of -1, so it's not the purely even R.
Right.
16 by 16 matrices.
So
I think so that's an issue. And one theorem I've heard is that there's like a generalization of matrix algebra where you have mixtures of evenness and oddness. So I guess what you do is you like take a graded vector space, a Z-mod 2 graded vector space. So it could like have n even dimensions and m odd dimensions.
Yeah.
And you could take its endomorphism algebra, and that will be a super algebra. So that will naturally, elements of its endomorphisms will naturally break into an even part and an odd part. So that's like the super mathematician's version of a matrix algebra. And so instead of just being indexed by like one number, it's indexed now by 2.
Yeah, I think that should probably work out very nicely. By the way, also, these.
Wait a minute, so the way it works.
Anyway,
so the way it works out, the theorem is that those are all Morita equivalent to the base field. So this R16 that that's my name for like 16 by 16. All right, 16 by 16 matrices over R. It's probably like some mix. Well, it's definitely some mix of even and odd stuff that should be notated more carefully. But it's still going to be Morita equivalent to real numbers. That was the point of all that stuff. I mean, by this theorem that I don't actually know the proof of very well, but it's probably, I think it's not very hard. So then the next thing I wanted to say was to notice that, like, yeah.
Sorry, I just have to ask, what is this notation? I didn't check the notation. T and C. What are T and C? What are the letters?
I don't really want to worry about those now.
Okay. I thought I was already supposed to be following that.
Yeah, no, that's like some extra stuff.
Okay, that's fine. That's fine.
So as we keep on throwing in these square roots of -1, we get these Clifford algebras, and for a while these Clifford algebras are equal to the superdivision algebras. That is, for a while they are superdivision algebras. But when they get to a certain size, and I think it's like right here, so like Cliff 4 is not the quaternions. That wouldn't have, notice the dimensions are doubling. 1, 2, 4, 8. So this has to have dimension 16. The Clifford algebra has to have dimension 16. So it's obviously not quaternions. So what it really is
so those little symbols are Morita equivalent symbols?
Yeah, those are Morita equivalent symbols.
Okay.
So what Cliff 4 is it's actually like 2x2 matrices with entries in the quaternions.
Mhm.
And from then on out, that is from 4 up to 7, the Clifford algebras are bigger than the division algebras. I'm showing the division algebras here, the superdivision algebras.
Uh-huh.
But these Clifford algebras would be like matrices of guys in the division algebras. Okay. So with that in mind,
Wait a minute,
I
is there a
guess-
typo here? Is there a typo here?
did you see one?
Well,
Where?
3 o'clock and 6 o'clock.
Sorry, 3
the
o'clock.
little-
I can't even see. I don't know
At
how to
at
count
6
this.
At 6 o'clock, was there supposed to
By
be?
6 o'clock, do you mean like mod 8 or in the usual clock system?
I meant a
Is
usual
this-
clock system.
Okay, that's 6 o'clock. It's 4 o'clock. Okay.
Yeah.
You're getting quaternions both times? Is that what you're
Yeah.
complaining about? No, it's not a mistake. So
What have I
there
screwed
are
up?
they
Let's
have
see, yeah.
they're different gradings. They're different Z mod 2 gradings. Also, the complex numbers is showing up twice.
Complex numbers is, okay, right. Certainly I know the complex numbers is supposed to show up twice.
So this is the purely even guy. This is the guy with one odd square root of -1.
Yeah,
This is the guy.
and by the way, that really fits with, a long time ago, somebody explained to me that the quaternions were just the tensor square of the complexes if you use the funny grading on the complex.
Okay, good. Well, that's what we're getting here. Yeah.
Yeah.
So this is the quaternions with, say, I and j being odd, and then ij equals k being even.
Yeah.
So this has like two-dimensional even part and a two-dimensional odd part.
Yeah.
By the time this other copy of the quaternions here, down at 4 o'clock,
Yeah.
is this is a purely even quaternion algebra.
Really even. Yeah. Okay.
Yeah. And so, but it's Morita equivalent to some kind of thing where you're like tensoring that with some matrix algebra, but it's like one of these super matrix algebras. So all the odds, so they have odd elements in them. So
Yeah, there really is a lot to think about here to try to get used to some of this. Go ahead, yeah?
Yeah, it's yeah. So basically here we're throwing in one square root of -1, odd one. Here we're throwing in 2. Here we're throwing in 3.
Yeah.
And the third one, you can actually take, you can like take 2 of those 3 and let's see, how do you do it? Somehow you cook up a square root of +1 out of that with these 3 square roots of -1. And when you have a square root of +1, that's like gives you a splitting. It's like a thing you can use to define a splitting.
Yes.
And so the fact that this is splitting is
Yes.
is due to that way of thinking
Yes.
about it. At a more simple level here, when we're throwing in a single, you could think this, yeah. So part of the weirdness about this, sorry, throwing even more weirdness stuff, I guess, is that you can also march around the clock this other way
Sure.
by throwing in square roots of +1. And
That's interesting.
and so if we take the real numbers and we throw in a single square root of +1, then we get r plus r, which is r with a.
Well, but then that means there must be
Splitting.
some very standard way that I'm forgetting at the moment to think of the matrices as generated by the 2x2 matrices is over the
Of complex
over the-
numbers.
no 2x2
Oh.
matrices of real numbers. Let's see.
Oh, of real numbers, yeah, as
It's generated
generated
by.
by. Yeah, there is.
I
So, like-
must have thought about that before, maybe not. But yeah, okay, go ahead. Sounds vaguely familiar, but not sure.
Yeah, there's. Well, like you can think of this as pretty familiar way, maybe to think about the complex numbers as special 2x2 real matrices, where I is this matrix with like a 1 and a -1 on the off diagonal.
Yeah.
So
Yeah.
you can do that to think of the complex numbers as special 2x2 real matrices. And then you can also throw in this diagonal matrix with a 1 and a -1 down the diagonal. That's a square root of +1. And then
I'll have to think
those
about
two
that, but
guys,
that sounds, yeah, that sounds, yeah, very.
yeah, those two guys anti-commute, if I have it correct. I hope they anti-commute. I'm getting confused about why they anti-commute.
Well, it sounds very plausible that they do, but I didn't check.
Yeah, I'm worrying that I screwed up. But those two would generate the 2x2 real matrices, and so that's.
I mean, what were
That's-
you worried that they might do instead of anti-commuting? Were you worried they might commute?
Commute is what I'm worried.
How could they commute? Maybe they
Because
could.
one of them is because the off diagonal one is not just switching the two entries, it's multiplying one of them by -1. But I guess that's no, I guess that's good. I guess that makes them anti-commute no matter what the other one is or something.
All right, that's
Yeah.
a homework they could check. Okay.
I have to. I'll multiply those 2x2 matrices on my own time. If I had my tablet, I can actually do matrix multiplication in real time, but not in my head for some reason. Well, not very fast in my head. So yeah, so actually, so like another, if you actually this reminds sorry, this is getting way too mystical, but when I'm like playing music, I tend to think of like the notes up to about the fifth of the scale as being like really basic things, and then the ones from the fifth up to the octave again, like namely the sixth and the seventh, as being sort of like more subtle and exotic. And I actually have the same feeling about.
I mean,
this stuff.
but what you're saying just bugs me that, you only go up to 7. It's a heptatonic.
I know, it's a fake. I know, it's really.
I mean, you could
crappy.
have an octatonic.
I know, you could. Yeah, I know. It's really irritating that, you hear about octaves in music and you want to like correlate it to this stuff and make all this wonderful thing. So it turns out that it's because they couldn't count. So they started counting at 1.
Oh, it's the old fence post thing, but okay.
Yeah, right. Yeah. I read about mathematicians saying like music theory is way too complicated. It'd be so much easier if you started counting, you called the unison 0 instead of 1. And then the octave would be called 7 instead of 8. And there's some truth to that, I think, but I've been studying a lot of music theory lately, and I now think of this as like stuff that people say who like are like the kind of people who want to find an excuse to give up right away, like at the first sign of anything that's like not like to their liking, they give up.
Well, there's some really fun stuff, but anyway. I mean,
I've been thinking about music.
Talk about music instead of math.
Yeah.
But go ahead.
Yeah. So anyway, so what I was sort of suggesting is that like up to here, the Clifford algebras match the division algebras, and then when you get down to here, it's like the Clifford algebra is twice as big, and so then these ones, the Clifford algebras keep on doubling in size, whereas the division algebras actually start shrinking again. So it's like getting a little bit annoying to think about, and so not that annoying, but if you find that annoying, then you can like start going this direction and throwing in square roots of +1. And so if you throw in square roots of +1, then those Clifford algebras do match these division algebras up to here. And then I think again, when you get down to here, you find that the Clifford algebra is bigger than the division algebra. So anyway, so if you like to relate the Clifford algebras and the division algebras, it can be good to like go in both ways around this circle. Yep.
I want to re-ask a question about that symbol that supposedly means Morita equivalence. Did you already probably warn me about this? That it actually means some kind of super Morita equivalence?
Yeah, it means, well, it's interesting. If you forget the grading,
Yeah.
it's true as Morita equivalents of algebras. But
I mean, I'm having trouble. I'm just confused about what was Clifford 4 is 16 dimensional. Oh, okay.
Yeah,
So you're
yeah.
saying this.
2 by 2 matrices of quaternions is what it is as an algebra.
Okay, maybe I just heard you say something. I heard wrong, something that you said right or something like that. Okay, that's okay. Okay, I think I was just making
there's
some silly arithmetic mistake or something like that.
Yeah, but there's a subtle point that you almost said, which is interesting, which is there's like two facts. You can work with these things just as algebras and not as super algebras.
Yeah.
And then the Clifford algebras are Morita equivalent to these to the algebras shown here.
Okay. Yeah. Okay.
Or you can think of them as super algebras. And then there's like the standard way to think of the Clifford algebras as super algebras. And then they are Morita equivalent to these algebras if you give these algebras the appropriate grading. And they can have multiple different gradings, which is why they're showing up twice. But you have to so you have to know which grading you're talking about. And so if you, yeah, so Milner's book on Morse theory has a really nice tour of the Clifford algebras and what he's doing with them is he's studying the homotopy groups of SO infinity.
Yes. I know to understand that stuff. Yes.
Or sorry, I should say like O infinity or U infinity for these two different clocks. And part of what's interesting about how he's doing it is that although he doesn't really emphasize it explicitly, what he's doing is he's taking these different Clifford algebras.
Yeah.
He's not treating them as super algebras. He's treating them as algebras, basically. And he's looking at their categories of modules. And he's basically, let's help I get this right. Some of the stuff he's doing amounts to like studying the K theory of those module categories. And so for example, let's like do one of them. So like take the real numbers. So then you take them, then you take the module category, you get the category of real vector spaces. And then there's this K0 of that, or Grothendieck. Sorry, K0. Wait, sorry. I don't want to talk about the Grothendieck of that. That's stupid. What am I trying to do? There's a way. What is this thing? No, I guess what I said Grothendieck group or something. But what I meant, I think, is you take like this is like the trick they do when they're like defining higher K groups. So you take somehow out of the category of real vector spaces, finite dimensional real vector spaces, you get your hands on the group O infinity. Or maybe I should say BO infinity.
Yes.
Is that good enough? I mean, I just like stuff I could say that I'm not especially prepared to say about how like the standard way that you get BO infinity.
Well, I mean, I'm not quite prepared to completely understand it, but I can fake the understanding.
You can fake it. Okay.
Yes.
Okay. So you get BO. I'll just say like there's a machine where you put in the category of finite dimensional real vector spaces, and out pops the spectrum BO infinity.
Yes.
I guess it's okay, now it's coming back to me. So there's a way to turn symmetric monoidal categories into spectra. And so we take, okay, so that's like the real vector spaces.
It's a kind of geometric realization of the so to speak.
So and then followed by group completion. So So we do that. Okay, we get BO infinity. And then what Milner does is he shows that like we can do that for any one of these different module categories of these different guys.
Yeah.
And you get different spectra.
Yeah.
And each one of those.
Wait.
They're monoidal with direct sum, by the way.
Oh,
In
monoidal
case
with
you're
direct
wondering about.
sum.
Yeah.
Okay. Okay, fair
So
enough.
they're not all, yeah.
Sure,
Yeah,
okay.
okay. Oh, I read your mind. Okay. Yeah.
Okay.
That's good. Yeah, no, it's right, because otherwise you'd run into trouble by the time you got around here or something.
Yeah.
So they're not all ring spectra, which is what the
Yeah.
commutativity.
Yeah.
So each of these spectra is like so then he shows that like each of these spectra is like the loop space, is the looping, or maybe the de-looping.
So in particular, you're telling me I shouldn't think of these as topological categories. I should think of these as categories and get spectrums that way.
I always get confused about this, but I think you do.
Oh, well, then we can put that
topology.
aside for worry about it later. But go ahead, yeah.
But I always get confused about this, but I think you do need the topology on the real vectors. You need to
Okay,
think of it as,
again, that's just an issue to figure out at some point, but I
Yeah.
don't have to worry about it right now.
yeah. So then what he shows is something like that each of these spectra, he doesn't even say the word spectra, each of these like infinite loop spaces is like the loop space of the one before it. And then that's how he shows ultimately that like the eightfold loop space of BO infinity is homotopy equivalent to itself. So he does it by this.
Yeah, again, I may not have ever completely understood this, but I always understood that what you're describing there is a big part of the point of trying to understand all of this. That
Yeah, for Milner, that's
these different viewpoints on dot periodicity really do just fit together perfectly.
Yeah. But then part of what's fun about it, besides sort of the general stuff, is that these 8 different module categories are all pretty charismatic and interesting categories. And the fact that what's something that he doesn't really talk about much is that because each of these Clifford algebras is mapped into the next one, it turns out you get adjoint functors between these module categories.
Sure, that seems reasonable. Yeah, sure. Yeah, that's very good.
And so they're all very charismatic. So like, let me just do one of them. So you've got like real vector spaces, then comes complex vector spaces. And so so one of these, I guess the forgetful functor, it's like the underlying real vector space of a complex vector space, and then that has the left adjoint, which is complexification. So that's like super famous. And then you have complex vector spaces, and then there's like modules of the quaternions, which I'll just abusively call quaternionic vector spaces. And then so you have like there's a quaternionification process and a forgetful functor. And then
What's
I'm gonna have what?
I was just wondering what you're
trouble. I mean, I'm groaning about what's going on with this one and this one. Now I'm thinking like maybe we do need to keep the superstructure around to even tell the difference between these two, but that can't be. I think I just made some interesting mistake or something, which I'll have to sort out, which has to do with the grading aspect.
Well, I forgot when we're talking about complexification. I already forgot the fact that this is the funny complex numbers with the funny grading.
Right. Yeah. So maybe to get this story to work smoothly, we really do need.
I keep on saying the funny grading, but that's not quite ready to say. It's the funny something. It's in the funny It's in the super world, and it is not super commutative. It's,
Yeah, so instead of funny, you can just say odd.
okay.
Yeah. So well, I need to like review this stuff of Milner's, because now I realize I'm like really confused about it. But
Sure.
but just going, but if I like evade the difficulties that I'm beginning to confront by going in the other way around the clock, if we throw it a square root of +1, then we get these split real vector spaces, or modules of R plus R as another thing. And I think that the idea of real, complex, quaternionic, and split, I thought it was supposed to be like that's basically about all you need to think about to understand all of these module categories and like their significances.
Say it
But
again.
clearly I'm
Three
confused.
things of what? Of real,
Complex, quaternionic, and split, where you could like throw split on top of real, complex, and quaternionic.
Yeah.
I had the impression that those were like like I was saying, that all these module categories are very charismatic things that you sort of almost heard about or almost heard about. So like you may never have really thought about split quaternionic vector spaces, but it's like sounds like something you might have heard about. So I had the feeling that like those were all the moving parts that you needed to know about to understand all these module categories. But right now I realize like I'm completely forgetting some stuff that makes me completely confused. Like why are we seeing H showing up twice here? And what are these two different categories that I'm alluding to with if they're both H here and stuff like that? So I think I can sort that out, but now I realize I'd better sort that out for certain purposes. Anyway, so this is basically all I wanted to say for now. I mean, I guess this is, there would be like some more fine-grained stuff like to really show how throwing in more of these square roots of -1 actually gives you these claimed results. I don't know if that's even something we ever want to do. There's a lot of other.
Say it again. What?
To do.
I blanked out for a second. Say it again.
I was just saying that like there's this thing that we could in theory do, which I don't know if we ever will want to do, which is to check that like throwing in these extra square roots of -1 produce the claimed Clifford algebras here. I mean, that's sort of well-known stuff, but anyway, there are a lot of other things I want to do more. And so the main thing I want to do is like understand why in the world should Clifford algebras have this like deep connection to superdivision algebras. And the other that I ran into just by giving this bumbling explanation of Milner's book on, it's actually his book called Morse Theory. That what's his description of these different module categories. So I realize I haven't thought about that for years and I need to think about that. So I'll stop.
I'm just trying to write down some notes and some things suggested. Well, I'm really tempted to. Well, first of all, let me just make a silly comment here.
Okay.
So at various parts of the discussion, we've been talking about vector spaces graded by an abelian group. I mean, you might have been saying something about other things graded by an abelian group, but you have been talking about vector spaces graded by an abelian group, and that just idly makes me think about the idea that, you know, and basically we're talking about finite abelians in this case. So vector space, well, I mean, we could be talking about other cases too, but mostly we're talking about, at the moment, we're talking about vector spaces graded by a finite abelian group. And even if it was by an infinite, there's still fun things you can do. But if it's vector space is great about a finite being group, then there's some sort of, I don't know what you call it, Fourier Hopf duality that's equivalent to, well, I guess depending on what kind of vector spaces, but in certain cases, yeah, okay, I'll think about that. Right, if it were complex vector spaces, then there would just be a Fourier duality kind of thing, making it equivalent to some kind of actions. But maybe I should think about what happens to that kind of Fourier duality if you're working over real vector spaces or something.
Huh. Okay, that's interesting.
That was my silly comment. But actually, I'm very tempted to say now to turn off the recording, because I'm not sure I have anything to say after this. So maybe this is the end of the discussion for today, because that was already very productive.
Well, I'll stop it now, and then we can talk about
whether to turn it back on.
Yeah. Okay. So let's stop it. Right. I'll stop it now.
Okay. And